Now to find the moment of inertia of the holosphere, we will consider that it is composed of infinitesimal circular rings. We will find the moment of inertia of the circular ring about the diameter of the holosphere, and then we'll integrate to find the total moment of inertia about the diameter. For which first we will draw the figure. Suppose this is the holosphere which has the mass m and its radius is r. And the elementary ring is drawn here, which has radius. By first we would draw a vertical line through the center, which makes angle theta with the vertical, and thickness makes angle d theta. So this is the thickness of the ring, and it makes angle d theta. So we can write that m is the mass of the holosphere and r is the radius of holosphere. So area mass density is, say, sigma. It is equal to total mass by total area of the holosphere. It is 4 pi r square. To find the mass of the ring, first we find the radius of the ring. This is the radius of the ring, and it will be equal to r sine theta using the trigonometry. So we can write that elementary mass of ring is, say, dm. It is equal to area mass density into area of the elementary ring. It is equal to m by 4 pi r square, and elementary area of the ring is its circumference. Its circumference is 2 pi, and radius of the ring is r sine theta. And its width is, this is the width, which is arc, and arc equal to angle into radius. For this arc, angle is d theta and radius is r. So we can write that width is r d theta. So it will be equal to m by 4 pi r square into 2 pi r square sine theta d theta. This r square get cancelled and 2 pi also get cancelled. So we have dm is equal to 1 by 2 m into sine theta d theta. This is our equation number 1. We know the formula of the ring for the moment of inertia about its axis through the center and perpendicular to the plane, and this is the I equal to m into r square, where m is the mass of the ring and r is the radius of the ring. We will use this formula to find the moment of inertia of this elementary ring about the axis passing through its center, and this will be di. This will be equal to elementary mass dm, and its radius is r sine theta, so it is r sine theta whole square. Now substituting the value, dm is 1 by 2 m sine theta d theta, and this is r square sine square theta. So we can write that it is equal to 1 by 2 m r square sine cube theta d theta. We have to find the total moment of inertia. So total moment of inertia is the integral of di, that is equal to integral of 1 by 2 m r square sine cube theta d theta, where angle will be theta equal to 0 to pi, which we can see in the figure. Here for vertical axis, here theta is equal to 0, and for opposite axis theta will be equal to pi, and for integration from theta equal to 0, it will cover total holosphere. So we can now calculate that I diameter for holosphere is equal to integral theta equal to 0 to pi 1 by 2 m r square sine cube theta d theta, 1 by 2 mr square is a constant term, so it is taken out of the integral and remaining is theta equal to 0 pi then sine cube theta d theta. To integrate it, first we will make some adjustments. This is, we can write sine cube theta as sine theta into sine square theta d theta, and it is equal to sine theta into 1 minus cos square theta d theta. This is equal to 1 by 2 mr square integral theta equal to 0 to pi, and this sine theta can be written in terms of minus 1 minus cos square theta into d cos theta. We can take this minus sign out of the integral, so it will be minus 1 by 2 mr square integral theta equal to 0 to pi 1 minus cos square theta into d cos theta. Here this cos theta can be treated as x, so we will have minus 1 by mr square, and integral will give integral of 1 is x, that is cos theta, minus, and this is x square, and integral of x square is x cube by 3, so we can write it is cos cube theta by 3, and in limits are theta equal to 0 to pi. Now we will substitute the limits. This is equal to minus 1 by 2 mr square. Upper limit, this is cos pi minus cos cube pi by 3. Then minus lower limit, this is minus cos 0, and then minus minus plus, it is cos cube 0 by 3. This is equal to minus 1 by 2 mr square. Cos pi is minus 1. Then it is minus minus plus 1 by 3. Then it is minus 1, and it is plus 1 by 3. So we will have minus 1 by 2 mr square, and it will be equal to minus 2 plus 2 by 3. This is equal to minus 1 by 2 mr square, and it will give minus 4 by 3. So it is equal to 2 by 3 mr square. This is the moment of inertia of the holosphere about its diameter. This formula is important and to be remembered. Similarly, if we have to find the moment of inertia of the holosphere about its tangent, so it will be equal to I diameter, and because tangent is parallel to the diameter, so it will be plus m into r square, where we have used parallel axis theorem. So it will be equal to 2 by 3 mr square plus mr square. So it is equal to 5 by 3 mr square. This is the moment of inertia of the holosphere about its tangent.